because like it's center at x equals 1?
Here, so let me just run through the whole thing real quick because everyone's kind of in different places. So the first thing, I didn't want you to build the Taylor polynomial from scratch. Use one of the two natural log ones that you can then make a substitution on to get what you want. So like I used the 1 plus u, and I said u is x minus 1. That way the 1 and the minus 1 would cancel each other out. I just have natural log of x. And hey, that centered it right where it was supposed to be. So there's my polynomial. Plug in a half. You got out the number. Then if we're estimating the error, well, it was third order, so it had to be n equals 3. So 3 plus 1 factorial, 3 plus 1 on the exponent. X minus a in here, your x value was 1.5, your center was 1. So then we just got to figure out m. Remember, m is a boundary on either side, positive or negative, whichever one's farther away from 0 of the fourth derivative, between the center and the point you were evaluating. So, since I know basically any reciprocal function is kind of what they're going to look like. Like you basically know it's going to either do something like this or something like that. I know negative 6 over x to the fourth is, well, it's going to be a vertical reflection of something like this. So it's going to do something like this in the area that we're curious about. If you don't believe me, graph it real quick. So it should be strictly increasing, but in the negative region. So I'm only going to bother checking the endpoints to figure out how I'm going to bound it. On the left side, it's pretty simple. Negative 6 over 1, negative 6. Therefore, the boundary, the absolute value, the magnitude would be 6. And I know if I go off to the right, I'm not even going to bother evaluating it because I know 1.5 to the fourth power is going to be bigger than 1. And 6 divided by something bigger than 1 has to be smaller than 6, so I got it locked up. I'm going to use m equals 6. And at that point, then it was number crunching. What time is it? Okay, cool. Is that reasonable? Does that make sense? So remember, m has to bound the next derivative between the center and whatever your x value was. So as long as the function doesn't have any shenanigans going on, increasing, decreasing, all that stuff, just check the endpoints, and you should be able to find your boundary. Nash. Derive natural log of x 4 times. So your first one would be like 1 over x, x to the negative 1, then negative x negative squared, positive 2x negative 3, negative 6x to the negative 4, make it 6 over x to the 4th. Abby?
In the parentheses beside the r sub 3, why is it 1/2 and not 1?
It should not be 1/2. It should be 1.5. I was probably in the habit of doing 1/2 from the previous problem. Because that was our x value. No, it'd be your x value, whatever your x value is.
You have to have the, because you have to find the m that bounds the m plus 1. So you wanted to grab, so we had to get to, and we knew it was between 1 and 1. So we checked.
If that was, I basically would just have to find the highest point and pick an m that is or lowest, the point farthest away from 0.
But still in between the center and
Right, yes.
Oh, that doesn't matter.
Yeah.
Okay. Yeah.
Okay. Okay. Our last one will be example 3 here. Then we'll stop. And we'll probably run out the clock for the weekend. So, I have seen AP problems that look like this before, so I was happy it came up in the book. And again, any of them that are labeled example, the author walks through. So if you don't like how we came up with it here, or you forget, you don't want to watch the video, you can go reread the book as well and watch him talk through it. So they give you a couple points. Here's our original functions point. Here's our slope. And like I was telling Abby earlier, sometimes they just give you some condition for the n plus 1th derivative. So that's what this looks like here. The second derivative, it's hard to see, but that is 2 tick marks. The second derivative is bounded by 3 for all values in the domain. Approximate something and estimate the error. So you will have to start from scratch on this one. But I'll give you a few minutes before I start working on it as well to try it.
Mr. Goulet, how did you know f double prime of 2 was m? Because that's the n plus 1.
M is always the boundary of the n plus 1th derivative. Here, if we're only using,
Not that way. F
Since we
prime.
can only do the
yep,
to every prime, the m plus 1.
yep. So the first thing we have to do is build our polynomial. You've got the original point and you've got the slope. Conveniently, those constants are divided by 0 factorial and 1 factorial, so you don't have to do any division at all. Here's your first order Taylor polynomial, which then we use to make our estimation. Plug in the 2.5. We get a number. And then our job is to estimate the error. Well, the error bound is, as you know, n plus 1 factorial, x minus center to the x plus 1 power. So since we only use the first derivative, we got a 2 factorial and we got an exponent of 2 on the polynomial term thing. And then the last thing we got to decide is what bounds the next derivative. Here, the next derivative is just the second one. And they gave us a number that bounds it. Nice. We're going to use that one. There you go. So AP will do that. Sometimes they'll give you a value. Oh yeah, the fourth derivative is always less than this, or bounded by this. So that's how they'll be sneaky about it, and then you don't have to pick that value yourself. But you still got to remember how to use it, so it works. This might seem pretty weak, just because it's only going out to the first power, right? But again, there's plenty of areas in STEM where approximating things, even without very much information, could be valuable. The example the author gives is, how about the GPS in your car on your phone? If you suddenly go into a tunnel, like the one that connects 435 to 69 Highway, you lose GPS signal for a couple seconds, right? But as long as your phone knows about where you are and about how fast you're going, and maybe at most how much you could accelerate, it could still give you a reasonable approximation for where you are. And at least it'd be good enough until you got out of the tunnel and you were synced back up. And I've got a couple people come up to me privately and said, Mr. Newell, I really don't get why we're doing this. Can you just go back and remind me? It's been a while, but this is kind of a spoiler alert for the end of the chapter. Well, I know this has already come. I've already said this to you, but I just want to remind you. Our goal is to be able to take something we can't work with and turn into something we can. For example, here is an integral that we cannot touch. Can't touch it. I mean, you can try u sub. Oh, shoot, I don't have an x to take care of my du with, right?
We have a calculator.
We do, but how do you think the calculator does it? How do you think an engineer programmed the calculator to do it? No, it was not, because you can't do it. But if I have a polynomial, if I have something that can model this, which, hey, we have a polynomial for e to the u, don't we? So we could sub in x squared into that model. And then if I could integrate that model, I should have the area for this thing that we can't actually integrate. So that's kind of another place where we're going with this long term. Why would we need to do that? There's a ton of equations that pop up naturally in physics and chemistry, just because those are my fields of expertise, that you can't integrate. And so your way around this is you make a polynomial that models the thing, and you integrate the polynomial. All right, the bell's should have rang 25 seconds ago. We are not going to do the next page. The next page here would be only interesting to you if you wanted a degree in math. So if you're thinking about a degree in math, you might actually pull up example 4 in the book and start reading through it. The practice for this, I want you to at least get started on this over the weekend. The practice is back on the title page. There's not a whole lot. It's 3 sets of 3 problems. We will quiz on Tuesday, so you don't need to be finished with the practice on Monday, but you should be ready to ask me questions. How about that? No, because I am still here.